Differential equations are among the most applied concepts in mathematics. If you look at almost any advanced book in engineering or science, you'll find differential equations on almost every page. They're everywhere. I'm going to give you three simple examples to give you an idea of what differential equations look like. The first one is one you've probably seen before in Calculus 2. Where you're trying to find the height of a rock, and let's say you're at the top of a 100-foot tall tower and you throw the rock upwards with a velocity of 20 feet per second, and you're trying to find the height as a function of time. That's with differential equations. You're not trying to find a number, you're trying to find a function, or more than one function. In this case, the function we're trying to find is the height of the rock as a function of time. And what do we know about the height? We know that the second derivative, the acceleration, is minus 32 feet per second squared. That's the acceleration of gravity at the Earth's surface. So we know we're trying to find h, and we know its second derivative basically. So it's this is typical. For application of differential equations, you know the derivatives or something about the derivatives or an equation involving the derivatives, and you're trying to find the function itself. In this case, we know the second derivative, the acceleration of the function. This is called a second order differential equation. The order of a differential equation is the order of the highest derivative. So if it involves second and first derivatives, it's called a second order differential equations. If it's only first order, it's only first order derivatives appear, then it's first order equation. Most differential equations involve first and second derivatives. You sometimes find higher derivatives, but that's pretty rare. Nearly always first derivative, second derivative. Here we know the second derivative is a constant, and all we have to do is take two antiderivatives. We're trying to find h given the second derivative. We take one antiderivative and we get h prime is minus 32t plus any constant. So it's not unique. You can add any constant. The derivative of any constant is 0, so minus 32t plus a, the derivative of that is minus 32 no matter what a is. Then we take another antiderivative to get h itself, and antiderivative of t is 1/2 t squared, so we get minus 16t squared plus antiderivative of a is at, and then we have another constant appears. So notice that we have two constants in the general solution because it's a second order equation. We get one each time we do an antiderivative. So the solution, just knowing that the acceleration of gravity is minus 32, it's negative because it's downward. It doesn't tell you what the h is. You have to know something extra, namely where you were when you let go of the rock and what velocity you gave it. And it's known that we were 100 feet above the surface of the Earth. H is the height above the surface of the Earth when time was 0, and the derivative, the velocity, was 20. That means we threw it upwards with a velocity of 20 feet per second. So from those two initial conditions, we can find a and b. When t is 0, this is 0 plus a, and that has to be 100, so a is 100. When t is 0, this h has to be, when t is 0, a has to be 20 because h prime is 20. When t is 0, h has to be 100, so 0 plus b has to be 100. So we solve for b is 100, a is 20, and there's our final answer. That's our solution of the differential equation with those two initial conditions. Typically, a first order differential equation will have one arbitrary constant, and you need one condition to pin it down. Second order, you'll have two arbitrary constants, and you'll need two initial conditions to pin it down. So now we know the height of the rock above the surface of the Earth at any time t, minus 16t squared plus 20t plus 100. So this is a pretty simple differential equation. Even though it's second order, you just have to take two antiderivatives. Unfortunately, most differential equations, you can't just take antiderivatives. For example, here's a equation for the balance m of t of your savings account, And what do you know about the balance? You know that you're earning 7% interest compounded instantaneously. That means at any time, the rate of change of your bank balance is 7% of whatever is there at the moment. 7% per year. So the derivative of m, this is another way of writing the derivative. We have two different ways of writing the derivative. H prime and dm dt is equal to 0.07 m. And that's first order differential equation because there's only first derivatives. M of 0 is the initial balance of the savings account. That's $1,000, let's say. And so you have first order equation of one initial condition. But now you can't just take an antiderivative because on the right hand side that's not a t, that's the unknown. You don't know what m is. So how do you solve this? Well, this is a little harder. We'll learn in the next section a systematic way of solving this kind of differential equation, which is separable. But here we can solve it just by thinking, well, we're looking for a function whose derivative is 0.07 times the function itself. Well, such a function is e to the 0.07t because what's the derivative of e to the 0.07t? It's e to the 0.07t times 0.07. And in fact, you can put any constant up front and the derivative of m is still 0.07 times the original function because you take the derivative of c e to the 0.07t. What do? You get c e to the 0.07t, that's m itself, times 0.07. So for any constant c, this is the solution. We'll, as I said, get a more systematic way of finding that in the next section, but we've solved the differential equation. Couldn't just take antiderivative because the right-hand side didn't just involve t. Now that's the general solution, has one arbitrary constant in it. To pin down the arbitrary constant, we use the initial condition that our savings account balance was 0 when we started at time equals 0. Plug in t equals 0. You get c times e to the 0, which is 1, and that has to be 1,000. Therefore, c is 1,000. Therefore, your bank balance m of t is 1,000 e to the 0.07t. That will give you the balance of your savings account at any time t now. Okay, now let's go to a third example. This time we're shooting up a rocket instead of a rock. What difference does it make? Well, the rocket is going to possibly go a long ways from the surface of the Earth. This equation here, the acceleration of gravity minus 32, only applies near the surface of the Earth. But if the rocket's out thousands of miles away, that equation is no longer valid. Now we have to use Newton's formula for gravity, which is the mass times acceleration is equal to the force, and Newton's second law says mass times acceleration is equal to force. Newton's law of gravity says the force is minus gravitational constant, universal gravitational constant g, times the mass of the Earth, capital M, times the mass, little m, of the rocket, over r squared, which is the distance between the center of the Earth and the center of the rocket. Now, this is a second order equation, but we can't just take two antiderivatives because there's an unknown function r on the right-hand side. We can't take the antiderivative if you don't know what r is. This is a much harder differential equation to solve. In fact, when we get through the course, we still won't learn how to solve this differential equation. It's too hard. It is actually possible to solve analytically, but it's very complicated. I can change this a little bit and make it impossible to solve. So here's an unfortunate fact about differential equations is most of them you simply can't solve. Not just you can't solve them by taking antiderivatives, you can't solve them, period. Analytically, you can't get a closed form solution. The solution of this may not even be possible to write in terms of elementary functions, trig functions, exponentials, logs, and so forth. It exists, but it may not be possible to find it, and even if it exists, well, we may not be able to find it. It may not even be possible to write it as a function of functions we've heard of. But it's a legitimate second order differential equation. We cancel the m, the mass of the rocket, and we get this. The gm turns out to be about 1.4 times 10 to the 16th. So we have second order differential equations. It's impossible to solve. We have two initial conditions. Well, almost impossible to solve. Two initial conditions. We know that at time equals 0, The rocket's on the surface of the Earth. It's blasting off, so its distance to the center of the Earth is the radius of the Earth, 2.1 times 10 to the 7th feet. And we're going to shoot it up with a velocity of 20,000 feet per second. Technically, this, I guess you'd say this is not really a rocket, because a rocket keeps the force acting on it continuously because it keeps thrusting. So really we're throwing the rocket up with an initial velocity of 20,000 feet per second and then turning off the rocket motor. So maybe it's really a rock, but anyway, it's going to go far enough from the surface of the Earth that this equation doesn't hold anymore. This one has to hold. So we can't solve it, or at least it's almost impossible to solve. So what do? Well, we're going to solve it numerically. What are we going to do in this course? We're going to find that most differential equations can't be solved like we did the first two equations analytically. So, but we will solve some of them. We'll solve a fair number. So there's some important ones that we can solve, and even the ones we can't solve, we can solve similar ones to give us an idea. But so what do we do in this course if we can't solve all differential equations, or can't even solve most of them? Well, besides we will solve some differential equations, in the next section we'll learn to solve a bunch of them. But we'll solve some of them numerically, that is, on a computer, approximately on a computer. This equation has a nice solution. You can get it as accurately as you want on a computer. We're going to use MATLAB. And that's one of the things we're going to do. That's called a numerical solution. And then we're also going to spend a good bit of time finding qualitative solutions. That is, we can, even if we can't actually solve the differential equation, we can tell some things about it qualitatively, and we'll start doing that in section 3. Notice that if the rocket stays near the surface of the Earth, then the gm over r squared, r will be pretty much constant if it's not going out into outer space. If it's staying close to the surface of the Earth, r will be constant at r0, 2.1 10 to the 7th feet. That turns out to be 32 feet per second squared. That's where this formula comes from. So this is like a special case of the more general formula for gravity, where the radius is pretty much constant. Okay, so the last differential equation we looked at, the distance of a rocket from the center of the Earth, was impossible to solve analytically. We won't be able to solve it even when we're through with this course, but you can solve most any differential equation using the computer. Here we're going to use MATLAB. We're going to use a MATLAB routine called ODE 45, which solves differential equations. It actually solves first order systems, so we have to reduce our second order equation to a first order system. Basically this means u prime equal r prime is the velocity prime, which is acceleration, is minus 1.4 times 10 to the 16th over r squared. So we have to we'll be doing this later, writing a second order equation as a system of two first order equations, because most differential equation solvers assume you have done that already. So we write a little function. You're not going to be using MATLAB in this course, so you don't have to understand all the details, but you can follow this pretty well. This is basically the system of two first order equations that's going to be solved by ODE 45. It's and the initial conditions, here's the initial r, which is the radius of the Earth, 2.1 times 10 to the 7th feet, and the initial velocity, which we said is 20,000 feet per second. Now notice I'm going to run it again with initial velocity of 30,000 feet per second and then 40,000 feet per second. So I'm actually running it 3 times. I'm going to plot the result each time, solving the equation, the second order equation, as a system of two first order equations, solving it 3 times with 3 different initial velocities. So as I said, this is really a rock rather than a rocket, because after we give it the initial velocity, we don't do anything else. We just let it go. A rocket would actually still be having the force acting on it. But so it's a rock that we're throwing up, a rocket we're throwing up with 20,000 feet per second from the surface of the Earth. And then we see what happens. Then we're going to try it with 30,000, then throw it even harder, 40,000. So here goes. And here is when we throw it up with 20,000 feet per second velocity. This is the surface of the Earth, basically. It goes up and then comes back down. Of course, right about here, when it gets back to the surface of the Earth, it won't really go on, the mathematics shows it going all the way to the center of the Earth, which of course isn't going to happen. So basically it explodes right there. Then we try 30, so it goes up and comes back down. We try 30,000 feet per second, and it goes higher and takes longer to come back down, but it does come back down eventually, and the differential equation goes all the way back down to hits the center of the Earth, which won't happen. Then 40,000 feet per second, and it keeps going up. Looks like it keeps going up forever, and in fact it does keep going up forever. It's the escape velocity is somewhere between 30,000 and 40,000 feet per second. If you throw it up faster than that, it won't ever come back, which that you can get an accurate a solution as you want for most any differential equation using software such as this ODE solver, ODE 45 of MATLAB. But this also shows one advantage of if you can solve an equation analytically, that's better, because, for example, here we could actually figure out what the escape velocity is without trial and error. We could pin it down by trying higher and higher escape velocity, so it's until it quits coming back down. But it's easier if you could actually solve it, but we can't. Now, we said we're basically going to do three things in this course. We're going to actually solve some differential equations, some important ones. In the next section, we're going to learn one of the most important methods for actually solving differential equations, so that's nice if you can do it. But most differential equations you can't solve. Even if it's just u prime equals a function of t, you've got to take antiderivative, and most functions you simply can't take antiderivatives analytically. So even the most simplest equation f prime equals f of t is usually impossible to solve analytically, much less if the right-hand side involves u, much less if it's more than one equation. But we will be able to solve some important differential equations. Now, the other two things we'll do some numerical solutions. We'll actually write routine to solve solve a system like the last, the third equation, the rocket that we're throwing up with a velocity of 20,000 feet per second. We use MATLAB to solve it, but you'll be able to write your own program to solve it using Euler's method later on. So we will be doing some simple numerical methods. You want more sophisticated numerical methods like the ODE 45 solver, you'll need to take different numerical analysis 4329 class. We have a chapter on solving differential equations, but we will solve some numerically. And the third thing is we'll get qualitative solutions. We'll be able to tell whether things are going up or down and so forth, and we'll start that in this chapter. Okay, but let's give an overview of what type of problems we're going to solve in this class. Well, chapter 1, the entire chapter is devoted to a single first-order equation, u prime equals some function of u and t, where u is the unknown function we're trying to find, t is the variable. And we're going to get some numerical methods, some qualitative methods, and some analytical solutions. But the whole chapter is just a single first-order equation. Starting in chapter 2, we'll talk about systems of first-order equations. And you should always have the same number of equations as unknowns, whether they're simple algebraic equations, linear, nonlinear, or differential equations. Like here, you're going to normally have the same number of equations as unknowns. So here, starting in chapter 2, we'll talk about ordinary differential equation systems. That means you're trying to find more than one equation, more than one function, and you have more than one equation. Here we have two equations, two differential equations, two first-order differential equations, because they only involve first derivatives, for the two functions u and w. We're always looking for functions. With solving differential equations, we're looking for functions. Here we're looking to two functions. There's still only one variable, t. So ordinary differential equation means the function or functions we're looking for are functions of only one variable. So there's only one variable. There may be only one function, one equation, or there may be more than one function, more than one equation. Should be the same number of equations as functions, but still only one variable. Then it's ordinary differential equation, because the derivatives are just ordinary derivatives, because u is a function of t only, so you don't have to say derivative with respect to what. You say derivative of u equals 3u plus 4w and so forth. Now, so we're going to spend all of chapter 1 talking about single ordinary differential equation. Starting in chapter 2, we'll look at systems of ordinary differential equations, still only one variable. Now, if there's more than one variable, if the function or functions you're looking for, here there's only one function, here there's two functions and two equations. But if there's more than one variable, like here u is a function of x and y, say, then you can't just talk about the derivative of u. You have to talk about the partial derivative of u with respect to what? With the second derivative of u with respect to x plus second derivative of u with respect to y equals x plus y. So this is a partial differential equation. We're not going to talk about these at all in this class. They're much harder, because your region is not just an interval. T goes from A to B. It could be a complicated 2D or 3D region, so much more difficult. We're not going to do those. Then you can have systems of partial differential equations. Obviously, we're not going to do those either. So this course is 1 and 2 ordinary differential equations and ordinary differential equation systems. That means there's always the functions are functions of only one variable, but there may be more than one function we're trying to find.